Hello and welcome back to another episode of the Oxford Online Maths Club, if I can get the name right. I'm joined again by Ittihad. Ittihad, say hi.
Hello.
Um,
Yeah.
Great to have you back on the Maths Club. We're going to do some maths today that I'm really excited about. Ittihad's brought some maths that, to be honest, I either didn't know or I'd forgotten, so it was exciting for me as well. Quick shout out to people in chat. Hi to Athena and Venkata, Celia and Raphael, anonymous people, Josh, Maya, Adam. We've just been saying hi at the moment in chat. If you're watching for the first time, great to have you with us. Nice to see you. You can join in this live chat if you're watching live by going to slido.com/OOMC or going to the Maths Club website, which is maths.ox.ac.uk/r/club, and clicking on the join chat link. Hi George, hi Ross, hi another anonymous person. You can be anonymous if you want to, you don't have to set your display name. And people are joining from all across the world. So yeah, it's sort of a place where people are talking to us about what's going on. There's going to be some polls for joining in with maths, and I guess you can talk to each other about maths if you want, if I remember to turn that feature on. There we go. I've now turned all the features on. Cool, right, okay. Last week I did a quick poll, so quick admin at the start, sorry. Last week I did a poll about further reading, and people said they would sometimes read the further reading. And then people said that they would read the further reading. I think it got a bit out of hand. People said they would read the further reading if I put X in it. So I ended up putting lots of stuff in the further reading. So I'd just like to apologise that last week's further reading was about twice as long as normal and included a lot of me explaining mathematics. Maybe we'll do something like this. And standard question for guests while we're getting everyone in the room. Standard question for guests is, what A-levels did you do? Yeah, what A-levels did you do?
Well, the answer is I didn't do any of those. I'm an international student and I did something from Bangladesh, so no A levels, I guess.
Okay. I think they've put :D on that, so I think they know that they're asking the question we always ask guests, even though you've been on before and got to say that you didn't do A levels. Maybe leave that mysterious. Like, ooh, no A levels at all. How's that possible? Oxford has so many applicants from all around the world, and we love you all. Right, okay. I'm just looking at some numbers of people coming in. I normally waffle a little bit at the start and waste time when we could be talking about maths. I'm going to do a very quick pitch of what's going on today, based on what Ittihad showed me of slides and bits of maths. Basically, this one's going to be for fans of prime numbers, which I think is quite a few of you because we've talked about prime numbers before. So fans of prime numbers and fans of complex numbers, which we haven't talked about so much yet, but complex numbers have come up a little bit. If you're a fan of prime numbers and complex numbers, then today, prime numbers that are also complex numbers and complex numbers that are also prime numbers and complex numbers at the same time, combine those two. And we're going to do some pure mathematics with that. Hi to an anonymous person who just says the word maths loads of times, and Rebecca. Right, okay. I'm going to switch to... I think that's enough waffle from me. The kind of ultimate version of this maths club is I don't say anything. We could just cut all the waffle and just people come on and do maths. It'd probably work a lot better, wouldn't it? Right, I'm going to shut up and I'm going to let Ittihad introduce Gaussian integers.
Yeah.
Over to you.
Yeah, as James was saying that the stuff that we're going to talk about is like primes and complex numbers, which is interesting because when we think about the number sets, like sets of numbers, we have like the natural numbers, and then we have the integers, and then if you branch out, we have the rationals, and then the real numbers, and then the complex numbers. So you wouldn't think that like the integers have a lot of stuff common with complex numbers, but the set that we're going to talk about today is like a merge between the two because it's not. It's a subset of complex numbers, but it behaves and works almost exactly like natural numbers. And we have primes in it, and we can divide and do like GCDs and stuff with it. And it's quite wild how complex numbers can be primes and like integers. So yeah,
Okay.
that's what we're going to do today.
Brill. Right. Let's start by reminding them about complex numbers, I suppose. So you need integers first.
Yeah.
So
Gaussian integers are numbers of the form like a plus bi, where I is like our typical complex number I with I squared equals to -1, the imaginary number. And a and b are integers, as in like normal sense, like 1, 2, or negative something, whatever. So if you think about the Argon diagram, the Gaussian integers are the lattice points. So we don't have an image of that, but it's basically the lattice points. Yeah.
like a square grid of points.
Square
Should have
grid,
drawn
yeah.
this picture, shouldn't we? Square grid of points. They're imagining it at home. Square grid of points with integer coordinates. Okay, have I got a bit here? Yeah.
Right. So you would imagine that the Gaussian integers have like the same properties of addition, multiplication, and subtraction as complex numbers, because they're kind of subsets of complex numbers. So we add two Gaussian numbers by their term by term, I guess, and we subtract it in the same way. In multiplication, we use the fact that I square is -1, and we just multiply it in the usual way. Is it like FOIL? No, multiplication isn't FOIL. What's FOIL though? I forgot what FOIL is.
Yeah, it is. It's first, outside, inside, last for multiplying things that are sums of two things.
Yeah, it's FOIL.
Okay,
Yeah.
First.
So
let's do it. First, inside, outside. No, can't do it. First,
yeah.
outside, inside, last.
Right. Yeah, something like that. So yeah, we use FOIL to multiply it out, and you use the fact that I square is -1, and that's how we get the product of two Gaussian integers. But you're all probably familiar with complex numbers, so you guys know that. So we'll move on to like more exciting stuff.
Yeah, I should say, like, we sometimes have some year 11s or people not doing further maths watching and who might not have seen complex numbers, but we're just going to be super chill about complex numbers today. You might have heard of the idea of just defining an I, so that I squared is -1. We're just going to roll with that, and that level of excitement of like, we'll see what happens next is going to carry through. Right? Okay, what are we doing? We define something called a norm of a Gaussian integer.
Mm-hmm. So the norm of a Gaussian integer is basically the square of its modulus. If you think about it in complex numbers, so the modulus is like square root of a square plus b square, where and the number is a plus bi. So we square that, so the square root and square cancels out, and we have the norm is like a square plus b square. And this norm is like a really important fact, like really important thing in Gaussian integers, and the fact that it's embedded within Gaussian integers allows us to prove a lot of stuff relating to squares, as we'll see in the later part of the presentation. So yeah, since it's the square of since it's the square of the norm, so since it's the square of the modulus, I always forget what the modulus sounds like. Anyway, since it's the square of the modulus, we have the norm is multiplicated. You can just show that using like some basic algebra, like you let alpha to be a plus bi and beta to be c plus di, and just multiply everything out and see that the norm, and use the definition of the norm and see that it's actually true. But that's pretty boring. So yeah.
So I guess you can think about that as like an algebra fact about what happens when you multiply a plus bi by c plus di. Or you could think about it as some sort of fact about what happens when you multiply complex numbers.
Yeah.
I would say at this point, because I remembered we did this formatting thing, that all the way through, Greek letters like alpha and beta, and I think the next one's warning thing, reconnected. Might have just gone down there. Don't know what happened. Gonna assume I'm back. I just got error messages. Right, anyway. I cut out, but I'm back. Right, cool. I wasn't saying anything interesting anyway. You multiply numbers together, and the norm does this. It's something to do with the distance from the origin. And distances multiply nicely for multiplying complex numbers. I am back, say people in chat. Thank you, people in chat. I've no idea what happened, which is scary, but you know, wouldn't be the math stream without something going wrong. Cool, right. I was saying Greek letters for complex numbers, Roman letters A and B for their components, probably. might have got that wrong at some point.
Yeah.
Okay.
Also, we're like one of the questions that I get is that why are we using the square of the modulus? Because the modulus makes sense as it's the length from the origin, but in this case, since we're interested in the integer properties of it, and the modulus isn't most of the time it's not an integer, it's an irrational number. So since we're interested in the integer properties, we always consider the norm in Gaussian integers instead of modulus. Yeah.
Okay. Right. Good. So we've got this concept of given some complex numbers, we've got this norm that measures kind of how far away from the origin they are. Okay. One more definition.
Yeah. We're building up on the definitions. So
yeah.
Anyway, a Gaussian integer is a unit if it has norm 1. So and the question is, can you find all the units? So should we give a couple of seconds for people to do that?
Yeah, sure. So we're kind of building theory here. I'm going to talk over while they're thinking about finding all of the units. We're kind of building theory here to kind of build something like prime number theory in these numbers. So someone in chat called Left Coset says a circle. I think they're thinking about a squared plus b squared equals 1. Sebastian's got 4 suggestions of numbers as well. So possibly there's some restriction on these being Gaussian integers. Yeah, so I could have done a poll for this because some people say circle, some people are putting some numbers. We're kind of building theory here that's going to turn into something that looks a bit like prime number theory. Maya's got it too. Good. Cool. Yeah, surprisingly not. Yeah, George says unit vectors. So just thinking of complex numbers like they're vectors, which is an interesting take, but I think it sort of works provided you want whole number components on your vectors. So we said that a squared plus a and b are integers. A squared plus b squared is then also going to be an integer. I think there's a comment that if we take the square root of a squared plus b squared, that might not be an integer. But luckily, a squared plus b squared, we're fine. So like 2 squared plus 3 squared, a-okay. That's a whole number. Mia, I think that one might have norm... I think that's got norm 1. That's got norm 1, but it's not got integer components. I just need to catching up people who say the circle as well. Okay, I'll show them units.
Yeah. Right. So the Gaussian integers, if you think about it in complex numbers, it's quite confusing because the complex numbers has a lot more numbers than Gaussian integers. So the unit circle would be the right answer if we were thinking about complex numbers. But since we're only thinking about Gaussian integers, the coefficients of the the number would also have to be integers, and the only ones that are integer coordinates and also on the unit circle are the 4 numbers 1, I, -1, and -i. Because if we think about the equation a squared plus b squared equals to 1 in terms of integers, then we know one of them has to be 0, because if not, then both of them are at least 1, because squares are always positive if they are not 0. And then their sum would have to be more than 1, which isn't possible. So one of them is 0, and the other one is 1 or -1.
Yeah.
So we have 4 possible cases, and all the 4 cases gives us 1, -1, -i, and I. So yeah.
I think everyone who said circle was kind of halfway there at spotting that norm means you're on that circle, and the restriction of wait, we only want whole number components was what gets us down to these 4 numbers. They're a bit like the role that 1 and -1 play in real numbers, I suppose. Might they include 1 and
I mean, in integers, yeah.
Okay. In the real integers.
In
a little bit.
Real integers. It's confusing terminology. If you call real numbers, then it's real numbers. We have to say real integers and Gaussian integers now.
Yeah. Okay. I'll try and be careful what to say Gaussian quite a lot. Right. Okay. So we've got some units. I think we want divisibility next. Yeah. So we've got this notation again. I think this has come up a couple of times on the live stream before, but if you've missed previous episodes with divisibility, here's some notation for complex numbers or anything, I suppose. I'm going to say this, alpha vertical line beta, and that means A divides B, or you could say A is a factor of B. I think people say A divides B because it's fewer syllables. A divides B if there exists a gamma such that you could find a gamma that you could multiply alpha by to make beta. And that's the definition for real numbers as well, for real integers as well. So you might write something like 2 vertical lines 6, because 2 goes into 6. With,
I think we have a couple of examples.
Oh yes.
Okay. Divisibility.
Oh yes. I've got a poll for this. So, question in Gaussian integers is going to be something like, if I give you an alpha and a beta, it's either possible that there's a gamma that you can multiply alpha by to make the other one, or there's not. What do I want? Do I want that? So yeah, here I want something like, I suppose for this definition we're talking about alpha, beta and gamma all being Gaussian integers.
I think there was a question about gamma being integer. It could be a normal integer. It could also be a Gaussian integer. Like yeah.
Oops. Trying to get back to this. Yes, we'd like gamma to be a Gaussian integer. Ooh. Yeah, gamma could be a complex number. Yeah. So Josh has asked, where is it on chat? There it is. Josh has asked, could gamma be complex? Yeah, maybe. That's fine. I suppose while we're talking about Gaussian integers, these complex numbers with integer components, we're not going to put any special relevance on the real ones. We're going to try and treat all of them like, yeah, sure, these are all Gaussian integers, and maybe look for a gamma being a complex number as well. Okay. Okay, right, so people are trying to do the division. If you know how to divide complex numbers, it's a little bit like rationalizing the denominator, if that means anything to anyone. It's a little bit like simplifying a fraction. I've hidden results. I might show them again in a moment. Let's have a think. We've got about 20 votes in already on people thinking, is it divisible or not? And some people in the Q&A are saying what the division is. I think it's time to reveal results in this poll. People have voted for yes, this is divisible. Mostly. So let's have a good look. So doing the maths to check it, we're not going to do this step by step on the board. But if you write out what would happen if you tried to divide 14 minus 3i by 4 plus 5i, then great news. If you rearrange that by multiplying top and bottom by 4 minus 5i, that's a sort of clever trick to turn the denominator into a real number, then you get pretty neat 1 minus 2i. Great stuff.
Yeah. There's also another way to approach this problem. You assume that gamma is m plus ni, where m and n are integers, and then you multiply that with 4 plus 5i. And if you do that, you get a system of 2 equations, because you have something with, I think like, I'm not going to do that in my mind now, but you get 2 equations where one of them equals 14 and the other one equals minus 3. And it's a simultaneous equation. And you will get solutions for that in like rational numbers, definitely. But the question is if you can get a solution in integers. And if you can, then it's divisible. If you cannot, then it's not divisible. That's another way to do the problem, but that's harder. It's easier to rationalize the denominator. Yeah.
Yeah, so I quite like that there's 2 ways of approaching this. One, to say, well, suppose that gamma exists and try and do the multiplication. Or the other way is, well, I'll rearrange that to gamma equals beta over alpha, and then try and find gamma directly. What's chat saying?
Yeah.
People. So we've got a new question on the board that I put up. I like so the first 2 votes to come in on this one, when I turned the poll on, came in immediately and for opposite answers. So either yes or no. And then the next 4 votes were also balanced. One of the options is now winning for, is this divisible by that? It's not obvious, by the way, is it? It's not like sometimes you see in the real integers, you sometimes see like 32. That's definitely a multiple of 2 because it's even. Maybe there's something a bit like that maybe something would obviously be a multiple of something else. We could think a little bit about how to spot the things that are obviously multiples of each other.
I think of it as like we as a human race aren't like modern enough to like think about Gaussian integers and divisibility like we think about normal integers. Maybe in the future people will just see, oh, well, 14 minus 3i is obviously divisible by 4 plus 5i. Would have even like
Well, I can't wait. That's that's not me. That's your generation has got to work that out. Maybe the people in chat who have done this very quickly. Phoebe saying that the calculator has a complex mode. I don't know what that means. Well, I think I know what that means. It means that calculators are getting even better than they were last time I checked. Maya's got an argument about the imaginary parts are the same. Is that a little bit suspicious? I wonder if you can make that work. Can you ever have something divisible where the imaginary part is the same? I think you maybe can, but I can't think of an example. Ooh, that's highlighted. Venkatha in chat has got an answer for what happens when you try and do the division. You had to go on this, right, making the slides as well. I've got something like this. Got different numbers to chat. Somebody's calculator has a mode 2 to do complex numbers. Crazy times. Right, okay. Chat was way more successful in the poll on that one for voting, but possibly because results were being displayed all the way along, so it was like a democracy thing of reaching consensus. I love watching. You can change your vote on the Slido polls, so people change as they go through. Right, okay, we should speed up a little bit. I'm not entirely sure we've got all the right numbers here. If anyone called me out. 81, 78. Well, should maybe have used mode 2 on a calculator. Right, okay. Point is, sometimes it's not divisible. Okay.
Yeah.
Got a theorem.
Yeah. So, well, the theorem is pretty simple. If alpha divides beta in Gaussian integers, then the norm of alpha also divides norm of beta. So yeah.
So
we go to the proof now.
This one you prove by, I guess, saying what does it mean for alpha to divide beta, and then going from there. So it's not terribly tricky to prove that if alpha is a factor of beta, then there is a gamma, and then working out the norms using the fact that norm of a product. It's a callback to a few slides ago. Norm of a product is the product of the norms. So here we've got an expression that says norm of alpha is clearly a factor of norm of beta. Here's even what you're supposed to multiply it by. Yeah,
this expression is in our real integers. So we know that n of alpha is divisible, n of beta is divisible by n of alpha. So yeah, that gives us the conclusion. And the nice thing about this theorem is that this gives us a really quick way to check if two numbers are divisible. It's a necessary condition for divisibility. It's not like sufficient. Like we can't say that if n of alpha divides n of beta, we must have alpha divides beta. That's not true in most cases, in a lot of cases. But if it's divisible, then the norms are also divisible. So if we find, if we are like asked to find the divisibility of two Gaussian integers, and we find that the norms are indivisible, then we can immediately say that they are not divisible. And if we look at the past example, like the last one with 14 plus, I think, the last example, 4 plus 5i has norm 41, and 14 plus 5i has norm, that's 196 plus 25, that's 221. And I believe 221 is indivisible by 41.
Okay.
Because 5 times 41 is 205? Yeah.
Yeah. Okay, okay. So the norms are going to be divisible. So there's a chat going on. Molly has responded to my concept of can you have numbers that are divisible by each other by having that have got the same imaginary part. Or the same real part, I suppose. And Molly suggested, hang on, if you take two numbers that are equal to each other, then they're divisible with gamma equals 1. And they have the same imaginary part and the same real part, which is true. I'm sort of imagining, can we do other ones as well? Maya wants to know if we're all good at mental maths, and Maya, we're not even sure that the maths we just put on the board that we thought about for ages is true. We might have got some of the numbers wrong, but I'm not sure. Also, I didn't want to add 196 and 25 together. I'm very glad that you did that. Right, okay. Where are we going with this? Right, we've got some concept of what it means to be divisible. We've got some checks for working out whether things are divisible or not. That's handy. I think it's time to tell them about primes.
Yeah. I think we were mentioning before, like how the units work as like 1 and -1 in integers. So here's where it is similar to that. Anyway, so we define the trivial divisors of a Gaussian integer alpha as 1, -1, -I, then alpha, -alpha, I alpha, and minus I alpha. So these are the 8 trivial divisors, and every Gaussian, like every non-zero, zero included, I guess. Anyway, every Gaussian number has these 8 divisors always. Well, if it's 0, then it's not like they're not unique, they're not different, and that doesn't matter. So yeah, every Gaussian integer has like 8 trivial divisors, and if you contrast that with the real integers, we have 2 divisors, like the number n and 1. So yeah, and we define a Gaussian number to be a prime just by saying that, oh, if it doesn't have any divisors except the trivial ones, then it's a prime, just like we do in the real integers. So yeah.
The only difference here is that we've got to ban more things for being trivial divisors. Like for the kind of positive whole numbers that you start with, you ban 1 and the number itself. Here we've got to ban lots of other things.
Yeah. But if you don't ban them, then there are no primes, which is sad.
Right. Yes. Because of what Molly said about writing any number as 1 times itself. Yeah, we still don't. We don't want that to stop it being prime. Okay. That's a definition of prime numbers. It kind of feels quite similar to the definition of prime numbers that you've seen before. We're going to explore some of the consequences of this definition next.
Yes, I forgot to mention one thing, that we can. This definition is also equivalent to defining it as a Gaussian integer is a prime if and only if it doesn't have any divisors of norm more than 1 and norm less than n of alpha. Because the 8 divisors here have norm either 1 or alpha. So if it doesn't have any other divisors with other norms, then it's a prime. Yeah. And that's a good way to think about the Gaussian primes.
Sure. So this norm function is handy because it tells you, it kind of gives you a way of looking between a number and 1, but sort of between a number and the origin, and sort of ring of numbers in between. Somebody said something very clever about quadrants in chat.
Yeah.
He's on screen, but I'm just going to point at chat. Okay. Weird consequences. Let's go. So, question on the board: is 5 a Gaussian prime? So, Gaussian primes are ones that I had that definition just now. Don't have any non-trivial. Don't have any non-trivial factors. Am I saying that right? Yeah. Don't have any non-trivial factors. Votes at the moment 2-1 for yes, no, yes, no. So I guess while they're voting, arguments in favour or against, 5's very much a prime number in the real integers. You could check all the numbers 1, 2, 3, 4. I guess don't check 1 because that would be a trivial factor. Check 2, 3, 4. None of those are factors of 5. But in the complex number world with these Gaussian integers, we've got more things to check. Got to check if that's a multiple of 1 plus 10i or something. Let's not check that because it's got massive norm.
So if it has a factor, then the norm, like we can think about the norms easier. So 5 has norm 25 because it's 5 plus 0i, right? So if it and we are interested in factors of norm less than 25 and more than 1 because otherwise they are going to be trivial divisors. So we must have the norm to be 5 if we want to find the non-trivial divisor.
I see. So you're thinking carefully about if 5 factorized, over complex number integers, then there's a certain property that the norms of those things would have to have, because you could write down the way it factorized is and think about the norms of each of the terms. Yeah. In fact, Molly and a user called UFD have submitted, and also voting. The vote is being, I think, massively won by people who think this is not prime. In fact, this is not a Gaussian prime.
Yeah.
That's the factorization we got. Is that slightly different from some of them? It's interesting, isn't it? Molly's got 2 plus I and 2 minus I, and UFD's got 2 other numbers. Interesting. So 5's not a Gaussian prime. Phoebe asks, is there a funky relationship between Gaussian primes and real primes? And yeah, it's very funky, I think. Is that true? Is it very funky? Am I overstating it?
I mean, it's unexpected.
Okay, I'll take unexpected. Okay, what's here? Oh yes. There's a note about whether you can quickly spot. So this is the thing I think you were just saying about, if it factorizes, then you can write it in terms of its factors, take the norm of everything in sight, and then you've got a statement about norms.
Yeah.
Okay. How do people work that out? I think probably people checked small numbers, checking small complex numbers, or complex numbers near the origin with small numbers in.
I think an easy way to work it out is to think about the norm, and the norm was 1, and we need the norm to be 5. So something squared plus something squared is 5. That means like we have the one option that works is 1 plus 2, 1 and 2. So then it works out.
And someone said it's like the difference of 2 squares, which is brilliant because it is the difference of 2 squares. It's also sort of the sum of 2 squares because it's 1 plus 4. So the sum of 2 squares is sort of the same thing as the difference of 2 squares if you're allowed complex numbers, because the plus and minus signs is just square of I. Anyway, okay, if the norm of an integer is prime, if the norm of a Gaussian integer is prime, then your number has to be a Gaussian prime because there's no way to factorize it. If you had a factor, then we would play games like this. Okay, not going to dwell on that too much. Right, okay. What's next? Oh yeah.
Yeah. So we're going to prime factorization now. Just like real integers have prime factorizations, they have unique prime factorizations. We might have that, I don't know. But at first we're going to show that every Gaussian integer can, with norm more than or equal to 2. So it's not an unit. It can be written as a product of Gaussian primes.
Yeah.
And the proof is quite similar to the normal one, if you've seen that. We go by induction, I think. Yeah, induction.
So my normal proof for this would be something like try to factorize each number. If you get to a number that you can't factorize, well, hang on a minute. That's either prime because you can't factorize it, or if you could factorize it, then well, great, you've factorized it in terms of smaller things. And the proof here works kind of the same way. I'm speeding up a little bit, so this is going to be... I'm speeding up a little bit so we can get to the cool bit coming up in a couple of slides.
Yeah.
So there's a proof by induction, which we'll go through really quickly. I know that people in year 11 or not doing further maths maybe haven't seen proof by induction, but it's going to be okay, don't worry. It's going to make total sense. So we're going to do induction. That means working systematically through the values of norm of alpha. Starting from n of alpha is 2. If n of alpha is 2, then that's, well, the norm is prime, so you're a Gaussian prime.
By the previous theorem we did.
If not, so then we do our inductive step to say, okay, suppose that if it's true up to norms up to k, assume this theorem's true for all norms up to k. We've done loads of work, got up to k, brilliant progress. Now look at the numbers with norm k plus 1. Okay. Yeah. So look at the next kind of ring of numbers, the ones with norm of k plus 1. The numbers there might be a Gaussian prime, in which case, brilliant, you're done. It's a product of primes, just write it down on its own. You found a huge number, it's prime, brilliant, that's already written as a product of primes. One thing is a product of itself. Okay, if it isn't prime, factorize it, and the factors have to have smaller norms. We already did smaller norms, so that way sort of reduce the new problem down into previous problems. Combine them together, write them up, and smash it all together. Completes the proof. I've realised that that's actually an example of. Oh, sorry, go.
Yeah, I think we need to mention that like the norm of beta and norm of gamma has to be more than 1, because if it's 1, then it's not factorizable. And since alpha is not a prime, we can always find beta and gamma so that the norm is less than equal to k and more than equal to 1. So yeah, that's pretty important. Yeah.
I should say, I guess the reason I'm glossing over the induction bits of this is the induction framework is not very interesting. This kind of key idea that you're either prime, in which case, brilliant, you're already a product of primes, or if you're not a prime, then break down the problem into, you've got factors. If you're not prime, break it down and look at the factors.
I think this theorem is like better thought as going down instead of going up. Like if we have the number alpha and then we break down into smaller parts, and eventually we'll have to stop because like alpha is a finite number. And when we stop, we have alpha equals to a product of a lot of primes, even powers of primes. So yeah, the induction is like good to formalize it, but it's better to visualize it going backwards. Induction.
Yeah, k
here is an integer. There's a comment there. So k is an integer because like it's the norm. So that's a good point. Like we're doing induction, so. I mean, we could do induction on Gaussian numbers, but that's a bit advanced. But we do know how to do induction on natural numbers, and we're doing induction on natural numbers by doing the induction on norms, and because norm is a natural number, so we are allowed to do that. So k is an integer only.
So we kind of included this proof because some people like seeing proofs of things. This is very much like what university maths lecture notes might look like, of sort of state theorem at the top says something like everything can be written as the product of some Gaussian primes, proof by induction, and here are the steps, and then there's kind of a key idea in there. And part of being a maths student is to look at these lecture notes which have got like the idea in and find like what's the most important idea, so I can remember how this works, and learn from the idea. The idea in here, you're either prime, in which case done, you're a product of primes, or we can factorize you in terms of smaller things. Right, okay. Rebecca was 2 slides ahead of us when Rebecca asked a while ago, is factorization unique? And I think Molly and UFD already know that factorization is not quite unique in Gaussian integers. Gaussian integers being ones with whole number coefficient.
I think they did the example in the comments already.
They did this already, right? Let's just show this. Let's show. Yeah, they've already seen this because we had 2 suggestions that were different. 5 can be factorized like this: 1 plus 2i times 1 minus 2i, or like this. And those are different numbers, but they're almost the same. They're the same factorization, but with some extra units in, some extra factors of just I, or plus or minus signs.
And like when we define primes in integers, like whole integers, like negative numbers as well, we always neglect -5 and -7 and the minus numbers. But they have the same properties as the positive ones. They're not divisible by anything except the units. And a similar thing is happening here. And instead of like minus and plus, we have like minus plus and minus I minus plus I. So we have like four units. And if you multiply the units, you multiply something by units, it doesn't really change the divisibility of it. And that's why we get like primes in 4 bundles.
I think that's a good way of thinking of it, really, that we've included complex numbers. We've also included negative numbers. And so 21 is, oh gosh, are these going to be primes? I think 21 is 3 times 7. Someone's going to tell me these aren't primes. 21 is 3 times 7. It's also -3 times -7, which we've included in our number system now. And somehow those don't quite feel like different factorizations. -3 times -7 feels a lot like 3 times 7.
21 is also minus 3i times 7i. Yeah.
Right. Okay. So we've got the minus sign problem, and we've got the plus and minus factors of I in there as well. -3i times 7i. Yeah. Okay. Because you've chosen some more units to put in there, and units do this thing of throwing units in everywhere can make it look like a different factorization. We're not going to prove it today because we want to move on and do a thing with this. But prime factorization is unique up to unit multiples of these units. So if you can rearrange the terms and multiply each one by units, so that
so
the
basically,
terms match up.
if you have two different prime factorizations, then you can in theory like line them up and then like link them so that each of them are unit multiples of the other ones, and so it's unique in the sense that it's up to unit multiples.
Yeah, and this might feel a little bit like we're pulling the rug out of your feet by saying, oh, this is non-uniqueness example. Actually, it's pretty much uniqueness, and that's because there are other systems, not this one, but there are other systems where things can go much worse. So that's why when it's like this and it's not too bad, you can just fix everything with units. That's quite good. There are other systems where things go much worse, and you have completely different factorizations that give the same thing. Okay, right. A little warning for that. Okay. Oh, right. Okay. Because factorization is kind of roughly unique up to units. If a Gaussian prime divides a product alpha beta, then you can factorize the number alpha beta, and that Gaussian prime must appear in one of the factorizations of either alpha or beta. So there's this property that if P divides alpha beta, then it must divide alpha or beta. From sort of that prime has to appear in one of the factorizations.
And even if that P doesn't like appear in the factorization of alpha beta like strictly, we can find one prime in the product of alpha beta, so that if you multiply it by an unit, we'll get P, and that's basically the same thing.
Yeah, maybe I guess. Yeah, maybe everything on this slide is true up to units. Right. Chat has gone very quiet, which they sometimes do when we're not making any sense. So I'm going to leave this as factorization is sort of almost unique. Not quite unique because of plus minus signs and factors of I flying around, but it's not too bad. Okay. Here's a picture of them.
Oh yeah.
I didn't warn you about this. This is what they look like. I made this on my computer in a hurry. The origin's in the middle, and then the black dots are where the Gaussian primes are. So along here, there's a prime here at 3. That's prime, and then 4, 5, 6, 7. Oh, 7's prime as well. Good, I did pick some primes earlier. 5's not prime. We saw that 5 factorizes. So there's no dot. You see where I am? No dot kind of in the middle here. And there's some primes everywhere, Gaussian primes everywhere else, scattered around in these pictures.
I think it's symmetric with the x and the y axis.
Yeah. It's got reflectional and rotational symmetry going on. Someone below said
also the like x equals to y line, I think, and x equals to minus y line.
Phoebe says you only need one quadrant. Someone else, said before. So yeah, it's got symmetry. I think in the line y equals x. That's not obvious to me what's going on there. Maybe I need to go and think about it. Something like, if you could factorize a number, then you can also factorize. So if you can factorize a number, you can also factorize negative that number. You can also factorize I times that number in basically the same factorization. Just put an I in one of them.
Yeah.
Do they get more spread out as you go outwards? Yes. We think. Oh yeah, this is part of the arc diagram. People are looking for lines of symmetry, which is pretty good. We only need one octant if we're doing symmetry in the line y equals x. Yeah, so we could be really efficient and just calculate the ones over here. Embarrassingly, I wrote the code for this in the stupidest way possible. So I didn't take advantage of any of these symmetries.
I think when Gauss first like set the numbers, like defined the numbers, he defined the prime factorization in terms of like quadrants. Like we take only primes from this quadrant, and then after doing that, we will just multiply by an unit at the end instead of like multiplying every number by units and thinking about, oh, they are equivalent. I guess Gauss didn't like equivalence classes that much, maybe.
Josh has asked, do they get further apart as they get further out? I'm not certain, but Jonah in chat, I forgot to mention, Jonah's here answering questions in chat. Jonah's a current student. Jonah's quite confident, so I'm going to let Jonah take that one in chat. I think they probably do. I think we know, sweeping statement, but I think it's probably true that we know less about Gaussian primes than we do about prime numbers, real prime numbers.
Yeah. Probably.
It's probably true. This is something like a prime number theorem for Gaussian primes. People are coming up with a conjecture in chat. So there's sort of natural questions to ask for natural coefficiented numbers. Right. I like the way they form these little blobs. Sometimes they seem to join up and make little Space Invader shapes. Right. Okay. Yes. Somebody says 45 minutes have gone by. Yes, that's true. And we would like to prove some number theory. Should we do that?
Yeah. Right.
I love this. We really should do this.
Yeah. So this is the fun part. We're going to use the theory that we built up for the last 45 minutes to solve a problem in real number theory, like normal numbers. And everything in the statement is about normal numbers, so it doesn't have any Gaussian integers at all, which is even more fun because we're using something that's not given in the statement, a completely new number system to just solve the problem. So yeah, the theorem says that if P is a prime number of the form 4k plus 1, so it could be 5, or prime is a real integer, yeah. For 5 or 9 is not a prime. 13, yeah.
I've got a couple on slide. 5 and 13 are primes of this form.
Yeah.
Then the claim is that those primes, the ones that are one more than a multiple of 4 in the real numbers, those can all be written as the sum of two squares.
Yeah.
Amazing. So like 5 is 1 squared plus 2 squared, and 13 is 2 squared plus 3 squared. It's sort of like baffling. There are no complex numbers in this theorem. There are no Gaussian primes hanging around in this theorem. It's even got the word real in brackets twice to clarify how real it is. Right, before we get real, we need to make things more complex. Should we do... I guess this kind of structure... The structure is that you've got a lemma. I'm thinking about the best way to introduce the lemma. Should we just throw the lemma at them?
Yeah,
Let's just throw the lemma at them. Okay, before we prove the theorem, I'm going to prove something slightly different. It's not going to be obvious what this has got to do with the theorem. This is a sort of different maths result.
Well, I mean, it's similar because we're looking for P equals a squared plus b squared, and we're proving something that's similar in like divisibility. We're trying to find, we're relaxing one of the conditions. Instead of being equal, we are saying it has to be divisible, but we're also strengthening one of the conditions by making one of the numbers 1. So it's interesting. Anyway, the lemma is that if P is a prime of form 4k plus 1, like the one we're dealing with in the theorem, then there is an integer n, which is less than P, and also that if we square it and add 1, we have that it's a multiple of P. Well, P divides n squared plus 1 is a simpler statement.
Okay.
Yeah. So we've done a lot of like non-constructive proofs, but this time it's a very constructive proof. So yeah, we take x to be a number, like we take x to be p minus 1 by 2 factorial. So like we multiply all the numbers from all the integers from 1 to p minus 1 by 2, and p is a prime of the form 4k plus 1. So p minus 1 by 2 is 2k. So that's obviously an integer. Then if we multiply, like if we square x, then we have this whole term, and on the second line we put a minus sign in front of each of the numbers on the second part, and that's equal because I think, yeah. So this works out because p minus 1 by 2 is itself even, yeah, because it's 2k. So we are multiplying each of the term by minus 1. So minus 1 to the power 2k, which is just 1. So this works out.
Everything's still real. I love this proof. It's very constructive. It's very much, here's x, we're going to square it, and it's going to turn out to have this property. Okay, so squared x, put some minus signs in here, and now because we're thinking about whether it's a multiple of p or not, or how it relates to multiples of p, I guess another way of saying p divides n squared plus 1 would be to say that n squared plus 1 is a factor of p, or p... I don't know what I'm saying. The thing that's about to happen.
Yeah.
We want to look at modular arithmetic again. We've mentioned modular arithmetic a little bit on the stream before. Essentially, we're going to think about remainders. If you haven't seen modular arithmetic before, zone out for 20 seconds. It's going to be fine. We're going to say that this thing is 1 less than a multiple of p, I think, and that's it, using some brilliant mathematics. Maya wants to know why we chose X to be like that, and that's a good question. It's because of the thing it's about to do. So here's the thing it's about to do. If we think about this, if we think about the remainder that this has when we divide by p, then because of how modular arithmetic works, we're allowed to go through every term in that sum, every term in that product, and say what it's equivalent to up to multiples of p. So I'm going to leave the first lot alone, but then for things like -1, I'm going to replace that one with p minus 1, which I'm allowed to do because those differ by a multiple of p, p minus 2, and p minus 3, and so on. And brilliantly, if you do that, so if you add p to each of these terms, then adding p to each of those terms doesn't change the remainder when you divide the whole thing by p. That sounds like a really complicated fact that would be hard to check, but in fact it's just a sort of standard thing to do in modular arithmetic. So if you've if you've seen modular arithmetic before and messed around with it a bit, then you're allowed to do this sort of thing, that's adding in multiples of p.
An easy way to think about it would be to think of the term like p minus 1 times p minus 2 times p plus 1 by 2 as a polynomial in p. Ooh. So if you multiply everything out, you just have the everything is a multiple. Like if you have p to the power something plus p to the power something blah blah blah, and at the end you have like the constant term, and the constant term is just the thing that we have in the that thing we have before. So and since we're doing like modulo p, all the p's cancel out, so they are like equivalent. I
agree.
Yeah.
I'm worried that sounded probably more complicated. I know why you're thinking about polynomials, by the way. So there's a maths course where we do loads of stuff with modular arithmetic and polynomials at the same time. So we train students to think about polynomials a lot for this. Anyway, punchline is on the screen. This is now the product of all the numbers 1, 2, 3, 4, 5, all the way up to p minus 1. Half of them are written in reverse order. But it's all of the numbers from 1 to p minus 1, and that's equivalent to -1 mod p by Wilson's lemma, which we did way back in season 1, episode 9. That's right, this is now an advert for a different episode of this show. So x squared plus 1 is a multiple of p, so p divides x squared plus 1. We'll actually do slightly better, so p divides x squared plus 1. We can actually do slightly better to get a number that's smaller than p.
Yeah, because I don't think x is smaller than p.
X is huge.
Large number.
X is really big. But it's sort of slight tweak at the end, and this is just sort of showing off flourish. We can even make this number smaller because in modular arithmetic, multiples of p world, we can subtract a multiple of p. We could keep subtracting p from our number, and it would still have x squared plus 1 being a multiple of p. So when you subtract a p inside here, you're really subtracting 2px and adding p squared. And those are both multiples of p, so it doesn't affect. P still divides this. So kind of like a little flourish on the end. Actually, we can make this number small, smaller than p.
We can make this even smaller. Like we can also have n is less than p by 2 if we want.
Okay.
Yeah, because like -1 and 1 is like, if you square it, we both sum to 1. So we can go to the negative numbers, but that's not important for our lemma.
And I love the way that in chat here, by the way, sorry, just to call that, Maya goes, why do we choose x to be like that? And then a minute later, Maya says, that's such a smooth proof, right? So it's like that switch of like, what are you doing? And then, oh, right, okay, that's all come together very nicely. We could have done this as our sort of final punchline, but actually we want to use this lemma now. So it's sort of brilliant insight that if p is of this form, then there is an integer n, such that n is less than p, and p divides n squared plus 1, which is not at all obvious. Uses Wilson's lemma in the proof.
So yeah,
we can now go and prove our theorem. Let's go. Okay, so first thing we want to do is use our lemma to say, well, we're given a prime of the form 4k plus 1. By the lemma, we know there is an integer n less than p, such that p divides n squared plus 1. Here's the best bit of the proof. I love this so much. It's the reason we've done the last 55 minutes of mathematics. Look at the n squared plus 1 and factorize it over the complex numbers. So you can't factorize that normally, n squared plus 1. You can factorize n squared minus 1, no problem. N squared plus 1, how are you going to factorize that? over the complex numbers, that's the difference of two squares. That's n squared minus minus 1. And minus 1 is a square number in the complex world. So we've got p divides n plus I times n minus I. Which is a perfectly sensible thing to say over the complex numbers. Do you want to do the next bit? Take it.
Yeah. So we assume that P is a Gaussian prime now. Then by our prime factorization theorem, we must have P divides n plus I or P divides n minus I. Because if P divides alpha beta, then P must divide either of one of them at least. But that's not possible because if we consider the fraction, because P is an integer, right? And we were like rationalizing the denominator, and we don't have to rationalize anything now. We can just divide it by P. And we see that we have the number n by P plus minus 1 by P times I. But n is less than P, and 1 is also less than P. So this obviously cannot be a Gaussian integer.
It's like the division we gave them earlier, but P is real, so it's easier to do the division. And hey, those things, that thing's definitely not a Gaussian integer because real and imaginary parts aren't whole numbers. Mm-hmm. Okay, so P is not a Gaussian prime.
That means we can write P as a product of two Gaussian numbers, where both of the factors are not units, since it's not a Gaussian prime. And since P is an integer, if we take the conjugate of P, we also get P, and on the right-hand side, we get A minus BI and D minus GI. So P is like, in one hand, A plus BI times D plus GI, and in the other hand, it's A minus BI times D minus GI, because it's like we're taking the conjugate here. And if we multiply these two equations together, we get P squared on the right hand side, and we get A plus BI times A minus BI times D plus GI times D minus GI. And A plus BI times A minus GI combines together nicely to give us A squared plus B squared. And then D plus GI and D minus GI combines together nicely to give us D squared plus V squared. So we do some stuff in the complex numbers, and we get back to like integers again, because this is an equation in integers. A, B, D, G, and P are all integers. So we do a lot of complex stuff and Gaussian integer stuff, and then we have a nice equation here.
Yeah. I've just realised this is a statement about norms, isn't it? You can think of that as the norm of each side, and then use the product E norm thing. Okay, so we factorise this, almost there. You can see an A squared and B plus B squared, the end is in sight. It's an equation in integers. We got back to the real world. They're both bigger than 1 because those Gaussian integers weren't units. So their norms are both bigger than 1. And they're both factors of P squared, because look, we factorised P squared as these. I don't think we've yet used the fact, so we remind ourselves that P is a real prime. They're both factors of P squared, bigger than 1, so probably P must each be P. In particular, A squared plus B squared must be equal to the number P. This is brilliant. I love this so much. Isn't that cool? Also, D squared plus G squared. D squared plus G squared is equal to P. But I think maybe it turns out that that's not a different way to write the prime.
No, that's not a different way. Because if you think about it, we have P equals to A squared plus B squared. That means P equals A plus BI times A minus BI. And if we divide A plus BI from both sides, we get D plus GI is equal to A minus BI. So D is A and G is minus B. So we get that information. And in fact, like we can do some other like math stuff to prove that it's actually an unique way to write it. And there's a nice story about like a Fermat prime, like a Fermat number. So like back in like 1600s, Fermat thought that all the Fermat numbers were primes. Well, Fermat numbers are defined to be, I think, 2 to the power, like the nth Fermat number is 2 to the power n plus 1. So the first one would be 2 squared plus 1, which is 5. It's a prime in normal numbers. The second one is 2 to the power 4 plus 1, that's 17, that's also a prime. The third one is, I've calculated that before, so it's 257 because it's 2 to the power 8 plus 1, 256 plus 1. Yeah, and that turns out to be a prime, like just leave me on that. The fourth one also does, I don't know how big it is, but the fifth one is pretty massive. It's like 2 to the power 32 plus 1. And I mean, I think it's like 10 or 20 digits. Anyway, I mean, 2 to the power 32, that should have 10 digits at least. Yeah. Logarithms. Anyway, so Farmer thought that was a prime, but he couldn't find any factors or like check out if it was a prime. And then, well, I mean, Farmer didn't go anywhere. So he just conjectured that all Farmer numbers are primes. But then Euler found that 2 to the power 32 plus 1 could be written as 2 to the power 16 square plus 1 square. So that's a way to write that number as sum of two squares. And then he found another way to write it as sum of two squares, which proved that this is not a prime number, because 2 to the power 32 plus 1 is a number of the form 4k plus 1. So if it was a prime, it would be a prime of the form 4k plus 1, and we would have that it has a unique way to write it as a sum of squares. But Euler found two different ways to do that, and that's how it's not a prime, which is pretty interesting because there isn't a mention of factors here, and you'd think that to prove something is not a prime, you will need to show that it has you need to find a factor of it. But instead, Euler did it by showing it's a sum of two squares in two different ways. Which is pretty cool. Yeah.
So the leverage you get of once you know that things can't be written as the sum of two squares in two different ways, then if you can find things that are the sum of two squares in two different ways, to sort of reverse the logic in a way and say, well, can't be a prime, otherwise it would disprove that thing I've already proved. Brilliant. Right, okay, just wrapping up. People in chat have rated that proof as 8 out of 10, which I think is solid for this live stream anyway. I think, yeah, I'll take 8 out of 10 any day. Right, okay. Very quick wrap up, just because we've got a wrap up slide. Oh no, I've got an example. 29. Pause the video for an example of writing 29 as the sum of two squares, but hey, 29 factorizes. Along the way, by the way, midway through there, we proved that primes of the form 4k plus 1 in the real world aren't Gaussian primes in the complex world, which partly resolved Rebecca's question from half an hour ago about how funky is the relationship between real primes and Gaussian primes. I can tell you that things that are one more than a multiple of 4 in the real world are not Gaussian primes. What proof would be 10 out of 10? I have to think and bring my A game for a 10 out of 10 proof, I think. Gaussian integers are pretty similar to integers in some ways. They're both examples of Euclidean rings, which we learn about at university with other extensions and other bits of theory around them about when you can do stuff like this that's a bit like prime numbers. And we've just got a rating in that I believe to be that one is, I think, not not a Gaussian integer, right? That's the second one. No, maybe it is the first one. It's the first one. A Gaussian integer, brilliant. Right, okay. So a quick intro to abstract algebra. Thank you very much, Ittihad. That's been great fun. One of the best things we've proved on the live stream, I think. Thanks for everyone for watching and sticking through trips to the complex world and back to prove things in the real world. Hope you enjoyed the mashup of complex numbers and real numbers. We'll put some stuff together for further reading in the normal place on the Maths Club website down there. So if you go down to the Maths Club website, that'll turn up on Friday. So if you check back on the weekend, there'll be more related stuff to read about. Possibly another bit of real number theory. Possibly some more stuff about complex numbers. Maybe a bit of both. And we'll see you again for another live stream in 167 hours. Anything you want to say to wrap up, Ittihad?
Complex numbers are fun, I guess.
Brilliant.
Yeah.
Right. Thank you very much, everyone. Molly's maths fun fact of the week is in chat. Rewind the video a little bit if you want to read it. Sorry, Molly, don't have time to read it out. Right, okay. Take care, everyone. Bye.